A black hole is a region of spacetime where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it. The theory of general relativity predicts that a sufficiently compact mass can deform spacetime to form a black hole. The boundary of no escape is called the event horizon. Although it has a great effect on the fate and circumstances of an object crossing it, it has no locally detectable features according to general relativity. In many ways, a black hole acts like an ideal black body, as it reflects no light. Moreover, quantum field theory in curved spacetime predicts that event horizons emit Hawking radiation with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is of the order of billionths of a Kelvin for stellar black holes, making it essentially impossible to observe directly. Black holes of stellar mass form when massive stars collapse at the end of their life cycle. After a black hole has formed, it can grow by absorbing mass from its surroundings. Supermassive black holes of millions of solar masses may form by absorbing other stars and merging with other black holes. There is consensus that supermassive black holes exist in the centers of most galaxies. The presence of a black hole can be inferred through its interaction with other matter, and with electromagnetic radiation, such as visible light. Any matter that falls onto a black hole can form an external accretion disk, heated by friction, forming quasars, some of the brightest objects in the universe. Stars passing too close to a supermassive black hole can be shredded into streamers that shine very brightly before being swallowed. If other stars are orbiting a black hole, their orbits can determine the black hole's mass and location. History. The idea of a body so big that even light could not escape was briefly proposed by English astronomical pioneer and clergyman John Michell in a letter published in November 1784. Michell's simplistic calculations assumed such a body might have the same density as the Sun, and concluded that one would form when a star's diameter exceeds the Sun's by a factor of 500, and its surface escape velocity exceeds the usual speed of light. Michell referred to these bodies as dark stars. He correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. Scholars of the time were initially excited by the proposal that giant but invisible dark stars might be hiding in plain view, but enthusiasm dampened when the wave-like nature of light became apparent in the early 19th century. As if light were a wave rather than a particle, it was unclear what, if any, influence gravity would have on escaping light waves. Etymology. John Michell used the term dark star in a November 1783 letter to Henry Cavendish, and in the early 20th century, physicists used the term gravitationally collapsed object. Science writer Marcia Bartosiak traces the term black hole to physicist Robert H. Dicke, who in the early 1960s reportedly compared the phenomenon to the Black Hole of Calcutta, notorious as a prison where people entered but never left alive. In December 1967, a student reportedly suggested the phrase black hole at a lecture by John Wheeler. Wheeler adopted the term for its brevity and advertising value, and it quickly caught on, leading some to credit Wheeler with coining the phrase. In the second part of this video we will learn the properties and structure of a black hole. Thanks for watching.